Okay. So after a short break, the next session is going to start. So we are delighted to have a Dr. Abbas Raza Ali here in this workshop. He is an experienced artificial intelligence expert, which is who is specializing in a speech and language processing, computer vision, reinforcement learning, meta learning, and currently he serves an AI leader at PwC UK. Before this role, he held the position of applied science leader with the government of UAE, and before that, he led the cognitive and analytical competency at IBM. And he also earned his PhD in the machine learning from the UK University. He further expanded his expertise through the postdoctoral fellowship in expandability and the generative pre-trained transformers at the Data Science and AI Lab, New York University, UAE, with over a dozen of published paper in the referred conferences and patent to his name. His current research interest is about reinforcement learning, ethical AI, and artificial general intelligence. Since 2017, he has been chartered statistician with the Royal Statistical Society and a chartered IT professional with the British Computer Society since 2010. Additionally, he is also a member of Operational Research Society and Royal Science Society. And the ongoing research interest for his, which is deep learning, reinforcement learning, and generative AI. And his talk is revolving around open conversational AI, generative AI platform for enterprises. So I would like to invite Dr. Abbas Raza Ali to present.
Thank you very much. Hi, everyone. I'm Abbas. And I'm going to talk about our platform, which we have developed. We did all the kind of engineering, applied research, and development in-house in PwC. So in PwC, we have three paths. There are two typical paths. One is OpenAI, which is GPT, ChatGPT, and these kind of stuff. And then we have Vertex, Palm 2, and these models with Google. And then the third stream is in-house development, or we can call it open conversational AI, open conv AI. So that's basically PwC's generative AI as a service platform for enterprises. So usually there are three options that enterprises they are thinking to get to, roll out Gen AI in their enterprises. This Convai, Open Convai, my interest in everything is revolve around business to business, enterprise level use cases. I don't focus on use cases like this is an add-on in Excel sheet or any consumer level things. So for enterprises, there are three options at the moment. Either they can go for the typical route, third-party services, OpenAI, Google, or they can go for open source large language models. They can use a base large language model, and on top of that, they can build everything. And the third thing is they can train their own LLM, which requires $6 million to $6.5 million dollars and this amount. So this is the most optimal approach, which you can see here. It's the open source LLM, because even if any organization is trying to train their own language models are always generic. They are trained on massively large scale data sets. They cannot be trained on an organization's data set. Never ever. So always we pick a generic model and then we fine tune it on different tasks. For example, we are developing different LLMs. PwC is a big four company, and they are I mean, they are specialized in accounting. So we have a accounting LLM, we have audit LLM, we have legal LLMs. So these are the LLMs which we have thoroughly fine-tuned from one base LLM. One base LLM, in order to train a base LLM or foundational LLM, it will take $6 to $6.5 million. In order to fine-tune an LLM on other data, it might take 500 pounds or 800 pounds or maybe 1,000, including infrastructure. Infrastructure maybe 10,000 pounds. So or even less. So that's basically the idea behind all these things. So that's the approach that we have adapted in Open Convai. What is the benefit? Why we started this initiative, and what we are achieving with that? So ChatGPT, it's a 175 billion parameter model. I call it white elephant. So that white elephant is basically requires up to 16, I think, H100 or even more compute to deploy it. Whereas the language models we are using or we have been using, they take less than 160 GB RAM. That means one or two A100 GPUs. So on the other side, they take a lot more less GPU compute because their parameter size is much smaller. The maximum parameters that we are using is 70 billion parameter model. We started from Flan UL2, Google's 20 billion parameter model. Then we moved to Falcon 40B model, which is trained by my previous company in UAE. And then we moved to Llama 270 billion parameter model, which is kind of under Apache 2.0 license. We can use it for enterprise or for commercial use. So the models are 10 times smaller than 175B. Then, I mean, their accuracy, Llama 70B is as accurate as the GPT-3 or Palm models are. And they are not far away from Palm 2 and GPT-4. Now, GPT-4 is trained on 1.8 trillion parameter. GPT-4 is 1.8 billion parameter model. That is not making a lot of sense. I mean, no doubt it's a good model, but my lens is enterprise level lens. So from enterprise use cases point of view, I mean, this is not a feasible model. Generically, I mean, it is doing very well. Being a researcher, I always appreciate this kind of modeling and effort and all of these. But from enterprise point of view, this is not the feasible option. A base model, which is not very huge, doesn't require a lot of compute. You can fine tune it on domain specific data. Can give you similar or even better accuracy than GPT-4, which is not trained on domain specific data. It can give you very close accuracy to GPT-4 or Palm 2. So that's what we are achieving, and that's what we have experimented on our legal LLM, on our accounting, audit, and other LLMs. So now, what we are achieving with all these things? Scalability. We can deploy everything, and we are deploying everything on clients within clients firewall. The model is there, everything is there, internet is disconnected, and all of their employees, they are communicating with that thing. confidential data, very confidential data, and very, very confidential data. You can increase very. I mean, this thing, this data will never leave the firewall of an organization. Why? Because we are using smaller models. We are using smaller models. Those models are scalable. Scalable means they can be deployed anywhere in any organization for even smaller use cases or bigger use cases. If they are scalable, they are secure. Scalable means they can be deployed within the firewall, means they are secure. We are minimizing the hallucination by doing a couple of things. Some of them you can see on the screen, some of them we are still, experimenting them. First thing is open-ended question and answering thing and closed-ended question and answering thing. We, don't encourage open-ended question and answering mod. So most of our things are, or most of our use cases are around closed-ended question and answering thing, where we have the enterprise level data and the employees or the customers of our client. They want to just ask questions, queries, or anything, want to generate anything around their own data set. That means closed-endedness. So you have Llama 2 or GPT or Chat GPT, these kind of models. You can ask any question. That's an open-ended, that would be dealt as open-ended Q&A problem. Now you are providing your data and then you are asking some question and answering. You are confining the overall search space of the large language model to your data, kind of at very high level. And then we are writing the prompts in the way that either answer this question or this problem, solve this problem within this data which is being provided, or simply say no. The data, either the data is insufficient or there is some other problem with the data, but don't hallucinate. So this is what we are. This was our step one. Then the step two was, we have a lot of data. For example, we did it with a legal LLM case. So we have 4,000 lawyers corporate lawyers in our PwC UK practice. They basically take a case. They spend almost 6 to 7 weeks to prepare a case, to find out the interesting insights, contradictory things, and everything. Now, what they are doing with this system, they are providing all of their files, 1,500 to 2,000 pages documents, to the system, and then they are starting the question. First, to understand the case. The case is basically summarize this case in like 3 paragraphs or 4 paragraphs or 2 pages. So first they will get the summary of these things. Come up with the contradictory sentences in the cases. So the something which is being discussed on page number 3, and things which are and the similar kind of topics which are discussed, but in some other sense, in like on page 1,300 or 1,400. Large language model will help you to find out those contradictions, anomalies, gaps, and there are all sorts of questions you can just which you can't even think a large language model can solve those things, and can help you in a structured step-by-step way, how you can in 3 to 4 days you can prepare your case in a better way than you were doing it earlier and spending 6 to 8 weeks. So there we gather data of a lot of historical cases. Then we used a question generation model and generated a lot of useful questions. and then we used our own model Llama 2 and answered those questions. And then SMEs from legal vertical of PwC, they have thoroughly reviewed those questions very quickly, because their questions, answers, citations, and everything, those were there along with the context. And they finalize it, and we put it in the system, and we transfer that data. Now, all the data, all the things that we are getting is tailored to our things. For example, in accounting LLM, wherever we were using bank, its meaning was wrong. We were getting wrong embeddings. So we trained our own accounting LLM, and similarly, we are doing these things with the other ones in order to minimize hallucination. Then any domain, it's a cross-domain thing. And the one very key thing is low carbon footprint. So at the minute, GPT-3, the energy that is required to serve GPT-3 can be used to provide electricity to 1,700 mid-size UK homes for a month. So that's basically the power, the energy consumption of GPT-3 with 30,000 GPUs. Whereas this model, this approach, we also call it as a green LLM approach. So again, there are a variety of use cases, anything around knowledge management, enterprise search, content and code generation, tabular data analysis, structured, unstructured images, then image analysis and generation, speech and speech recognition and text-to-speech. They are just input and output sources. So those are there as well. But these are some of the key things. I think there is a question. No, it is created. It is one of the use case of Convai. Convai is using Llama 2, and yeah, the foundational model is Llama 2. Absolutely. Okay. Now let me get back to this one. So because we are doing everything, we have to manage everything. In case of GPT-3 or something, you can just put the key in your code and you can start doing things. You don't know how it is being served, how it is managing quantization, mini badging, model loading, and everything. So we are using 2A100. Even we have deployed this Llama 270 billion parameter model. You can use the mic and feel free to ask question. Yeah, okay. I mean, they can ask question, just use the mic and you can ask question. It's just an informal discussion. So we have tried a couple of things, TGI, faster transformer backend with Triton. We are using VLLM to deploy that model so that we can use minimal memory, because GPU is considered as one of the most expensive compute if we are not considering quantum computing, because quantum computing is not out there yet. So how we can use minimal GPU memory to deploy our model and serve at scale. So quantization. So now if we are using bits and bytes, if we are using 4-bit quantization, that means we are losing the precision of our weights. What is a neural network? A set of weights, a matrix of weights and nothing else. So weights are everything. If you are reducing the precision of the weights, that means you're it is directly proportional to the to reducing accuracy of the model. So we are using float 16B quantization, which is the optimal one and best for the machine learning based model. For example, it has one integer bit, and then I think 14 floating point bits, because most of the weights are in 0 point something and that bits, unlike a typical float 16b, where 8 bits are, I think, if I'm not wrong, 8 or 7 bits are assigned to the integer bit, 1 bit is signed bit, and the other ones. So with float 16b, we are using very consuming very less memory, and we are deploying at scale. And obviously, flash attention v2 and couple of other mechanisms we are using to minimize the latency. So this is our typical approach. For example, question and answering. This is our backend, where we have vector databases. For vector databases, because everything we are doing, so we are not using OpenAI embedding, OpenAI things. I never heard of OpenAI as well. There are a lot of third parties out there. So the idea is we are using our own embeddings. So BGE embedding is one of the best. Then we were earlier using sentence transformers and other ones. And then open source databases, for example, FAISS and other databases we are using to manage our embeddings. Then fine tuning, obviously, this LoRa PEFT fine tuning is one of the best one, where we have base model. I always call it as convolutional neural network style fine tuning, where we freeze the entire network. We don't retrain the network every time when we have to transfer one network to the other domain. We only fine tune the last fully connected layer, which is very thin layer. It takes a few minutes, and it helps you to transfer your existing network from one domain to another one with a reasonable accuracy. So similarly, you have one model, and then you add one thin layer, and you use all the pre-trained parameters, which were earlier pre-trained on web scale dataset, and then you provide your own data and all the parameters in journal and in layman's term, they are molded on your data or your problem. Another benefit of this PEFT LoRa is we only deploy, for example, there is a UK-based client, and they have 3 different departments: HR, finance, and service desk. Their domain is totally different. So what we are doing, we have deployed one single large language model, because it is really expensive to make copies of large language model in the enterprise world. Managing these 3 large language models differently for every organization. And you know what organizations they are doing? There is a 2-dimensional thing. For example, number of organizations and different systems of the organization. They start from one department, then other department, then other department. I call it, I mean, ever, this would be the largest transformation that is going to happen. One after the other, they are companies, that is in their roadmap, or they have already started doing it. They are moving to generative AI very slowly, but at least wherever I'm working with the clients, I always go with a step-by-step approach. For example, one department, 2 months trial, get some question and answering, adapt your system, see the accuracy, where it is going, employees training, their mindset, and changing their way of working. All of these things. I mean, this is a whole journey. But idea is in their roadmap. If a CIO or CEO is convinced to use Gen AI, all the departments they in all the departments they try to deploy. Now, moving forward, there is one large language model, and then there are thin layers. one layer for HR, another layer for finance, another layer for other systems, which is very, very much economical. And even on product fine tuning or adaptation is also possible, because it is only taking a couple of hours on massively large data even to update this thin layer on the newer data. And we usually start with the an update of this layer after every, or adaptation happened after every 3 months. So we can later, maybe we'll reduce this frequency, but this is the frequency for now. So this is our very simple system where we have conversational bot, we have content generation, knowledge management, tabular data, and everything. And we'll see this demo and after this one. So comparing with the OpenAI, so GPT-3, 4, and we are using Llama 2. It's 175 billion parameter model, the minimal one. We are using, in fact, 70 billion parameter model, and we are waiting for 34 billion parameter model, which would be the optimal one GPU deployment, and that's it. Zero short learning, we are doing few short learning in a lot of cases because we have automated all the fine-tuning tasks, synthetically generating actual data, question generation, their answer generation, and then very quick parse of review, and then fine-tuning it on the domain-specific data. And then PEFT LoRa is generic thing, which we are applying. They are using a lot of GPUs to serve, masses, but we are using maximum 2 A100 GPUs with 80 GB each. They are consuming 552 tons of CO2. I know this is not apple-to-apple comparison, but here it's 0.00 something tons of GPU. So our system is open source. They are taking 8 to 16 H100 to deploy one instance for very few people. We have tried it on Tesla T4 128 GB, A10G, and also A100 with support of Flash V2 and rest other details. And our model is very simple. That is the key thing. Hopefully very soon Llama 2 70B with the 30K 32K window context window will be there. We are charging on a per request based, whereas other models, cloud-based models, they are charging based on per token based. For example, how many tokens you are providing in the input and what is the outcome. Output token generated and input tokens which you are providing. So they are charging this thing is complex. So if you are generating very long paragraphs, it will cost you a lot. So that was the thing. Now let's see some demo. How much time do I have? 15 minutes more, or until I think 10:30?
So you have time.
Okay, great. So thank you very much. You can go on mute. So these are some of the things. And then I will go to the actual demo. For example, these are the files which you can see. We were working with the client. So we have selected a client, means we have selected a vector database, and then we are asking a question regardless of the length of this one, length of the generation, but input length is for now 4K only, context window. So very accurately, you can see that 37% reduction. What is their net zero strategy, and everything from I mean, almost 1,500 pages, which were there in 4 or 5 documents. Now they are comparing Sensbury with other competitors. Here you can see these are the citations. Here you can find Tesco's data, you can find BFC data, you can again find Tesco's annual report, Sensbury annual report, and they are comparing it. And there you can see that they are comparing that Sainsbury is there, and Tesco and Walmart and other Waitrose and other companies, they stand there. Then I think, yeah. We have submitted it to the client. So Tesco as the Morrison's, Sainsbury, and then their strength, weaknesses around the Nectar 360 system, other areas you can easily, I mean, analyze then recommendation. Can you see this, the response generated by the system? It is very detailed, very thorough, because we don't care about the generation, unlike chat GPT or other ones. I'll accept your invites later. Okay, so this is again a very useful prompt, very complex one. So just one more video, and then video demo, and then we'll switch to the other one. Please feel free to send the prompts if you want me to run any complicated one. You can just throw it there on the chat window. So this is basically using yeah, this one we deployed it for one of the largest chain in the UK. We were helping their teams to generate test scripts. So there was a company that they hired who was generating the test scripts. They were not happy with that. They were facing a lot of problems. Then they started using our system, and they were getting very thorough step-by-step system to test it, to generate all these things, which you can see on your screen. So additional security testing app, if we can include it for healthcare systems. GDPR is EU's, and HIPAA is US standard. Okay. So this is a prompt, UAT test scenario, and this is an actual scenario which I'm showing here. Actual means we have verified these responses. I cannot disclose the name of the client, but it's one of the largest in US and here as well. Okay. So similarly, this is our system. I mean, here you can see this is the same prompt I was talking about, and it's exactly another very good thing with the Llama 2 with Falcon. We were observing very inconsistent response. At one time, we were getting very small response, and it was talking about some aspects of the thing, and at very next moment we were getting very long response, and it was discussing, I mean, everything which is going on this earth, Pluto and Jupiter. So that model is really consistent. The responses are not varied a lot. Then here you can see we were working with a UAE labor Ministry of Labor, and we ask a question that online weaknesses of labor contract articles and suggest mitigation strategy. Basically, it is on open source, publicly available data set. You can find it on the web. So we got weaknesses in their labor law, lack of clarity and specificity in the contract terms, mitigation, ensure all the this thing, this. Then another weakness, unfair and one-sided contract terms. This is very interesting one, which we found in the UA, and this is the mitigation. Then weakness, lack of consideration of charging this. Then weakness, another one, dispute. In case of dispute, it is also one-sided thing. So we are extracting the citations, the summary, and everything. I mean, can be find here. Similarly, for structured data analysis, for this image annotation and everything, you can find it here. An image of PwC ML office covered in snow. Sorry. I'm sorry, actually, it messed up. I was just working on it before this call. So basically, this is the demo, and I mean, these are the things. It can do a lot of things. So one last thing, and then you can start asking questions. At the minute, we are working on predictive analytics, descriptive, predictive, and prescriptive analytics. That was in our I mean list. So in descriptive analysis, we have already achieved the things. We are generating the queries and everything, and then we are getting the results. In predictive analytics, we are using controller LLMs, and then using different agents, we are generating the data first. For example, how my revenue would look like in next 2 months. So generating last 2 months data, let's say, and then um, followed by the second agent is code generation. Either you can fix the code of forecasting, classification, or other models, or you can generate the code using code generation. But we have fixed the codes, and using controller LLM, it is basically selecting that whether user requires forecasting, classification, segmentation, or regression approach. And then in last agent, basically providing all the data to the model and extracting the result. And similarly for recommendation system, that this is the area we need to maximize. Satisfaction needs to be maximized, cost needs to be minimized, and then sale needs to be maximized. So what are the agents who are good in all these things? So multi-objective optimization, very simple kind of problem. GenAI can easily, I mean, solve this problem without putting any effort. So this was the presentation. Feel free to unmute your mic, and we can start discussing anything.
Yeah, hi Abbas. I have posted my question in the chat box. Like, I wanted to know, like, when somebody decides to go with models available like ChatGPT 3, 4, and otherwise train a model of your own, like how you present it. And I just need a figure in dollars per year. Like consider a test case. You have a 100-page data set, and the team and the expenses you have to include while train your own model. And I just need a figure in dollars per year, like how much. If you are exceeding this much per year, then we should go for preparing your own, like training your own LLM.
I mean, training your own LLM or fine tuning your own
Yeah,
LLM?
sorry, yeah, fine tuning in that
Fine
sense.
tuning. Yeah, there is a lot of difference in both of these things in terms of this one. Training means from scratch. Fine
Yeah, yeah,
tuning.
yeah.
Great.
Correct.
So
Fine tuning.
in here this question is for open source models or for closed source models.
Like when you use open source model, Llama 2 you're talking about, right?
Let's talk about it. How much would it cost for open source models? 70B is a reasonable one. You need two GPUs and maybe
Okay.
some AVM. Uh,
Mhm.
7,500 USD is the 24 hours. If you are using the model, that's the cost of serving
Seven
it.
7,000 USD.
7,000 USD is the cost to run the model. Uh, on the other side, what we are recommending, or what Middle East is doing mostly, they are just buying GPU, and it is costing them much less than this one. You can also use, for example, down the road, hopefully in a month or 2 months time, 34 billion parameter model will be there, and you can reduce it. But for the enterprises, this is nothing at all. So 7,000 for the infrastructure, and then you need some development, some one-time development, one-time thing, and for the synthetic data generation. No, not synthetic data generation, but in a synthetic way, generating the fine-tuning data. That's one script, and the other one is to fine-tune this one, which I think Shanti worked on it, and his work was around the similar lines. So for these three things, I don't think that it would cost you $20,000 or $25,000, even much less than that, in order to fine tune your model and to serve it.
Yeah, $25,000 one-time cost to prepare my own model or fine-tune my own model, which is a 100-page data set, or it can be, yeah,
Absolutely, absolutely. And then I told you that
$20,000. Yeah.
it would cost you $7,000 dollars to serve your model on monthly basis, 24 hours. And if you are not using for 24 hours, just like for some clients, it might cost you $3,000 if you are using it for 9 to 5, 5 days a week. And you have applied some jobs that just turn off everything after 6, and after 6 employees will work manually. No GPT after 6 or before 8 o'clock. So you can simply divide the cost by 2.
Okay, let's assume $3,000 per month or per annum, like
$3,000 or $4,000 per month
per month. four
for
thousand
serving.
dollars per month. Okay.
Okay.
So yeah, this is my running cost if I don't
Running cost.
fine tune my
Running cost.
own model.
20,000 roughly, and then 20,000 or even minimal cost. Maybe my rates or rates which are applicable here are a little bit high, but on average, and then running cost 4,000 if you are running it for like this one. Any other point?
Nah, yeah, thank you. I have one more
Go
question. I may be very naive, but I'll just put it I understand GPTs training fine tuning model. They give a better way of responding, like human. They sound like humans, like while they respond. But how preparing like 100 page data set and prepare a vector database and just query from the vector database, how.
Though I have already answered this question, but again, because it's a good one. You have 100 pages data set.
Correct.
You cannot straight away throw that data set for the fine tuning. You need to, if you want to use it as a Q&A kind of use case, you need to extract question and answer from this document.
Exactly.
There is a question generation model. Either you can
Mm.
use question generation model, MS Marco or something. On that data set, you can find the models, or you can use Llama 2 to generate the question. For example, you can chunk your data and then ask it. Sorry.
I think, Upendra, if you have any more questions, you can write down the question. So,
Just
Yeah,
wait,
sure, sure.
I can finish it. You need to prepare your data, generate questions, and then in the typical way, you can get the answers of those questions using GPT, and then you can provide that thing to the model. So that's a way. Rest you can, I mean, anytime you can send me an email, and I'll help you with the scripts with other things. What
Yeah, thanks a lot. Actually, I got it like figure to look at like when going deciding. Thanks a lot. Thank you.
what is the acceptance rate of descriptive as well as predictive models among the core finance people? It's little bit earlier, at earlier stage. Descriptive analysis is very good. We are providing reasoning, we are providing query, we are providing its reasoning step by step as explainability of our generated response. So my experience is the teams who are using descriptive analysis, we are providing Google style bar. They ask a question. I mean, they are not involving any BI guy, any data warehousing guy, anyone at all. Databases are there, and they can ask question and they can get the responses. It is acceptance rate is good, quality is very reasonable, and they are using it. I mean, frequently for like last 2 or 3 months. Predictive analytics, uh, uh, it is a little bit new. In experimentation phase, we have rolled out forecasting models. So you can ask anything that this is my variable. Please also consider this, and this variable as a independent variable, and this is my dependent variable, and extrapolate this independent dependent variable revenue, or anything which is around that. So just extrapolate this variable for 2 months, for 3 months, and you will get the answer. And I already told you that we are using controller LLM, which is parsing the query and then splitting it into 2 or 3 phases. For example, this part of the prompt is around data extraction. This much data extraction is required. And then once data is extracted, we need to pass it to this model. Agent 2 will generate the code for the model, or you can straight away you can hard code very simple forecasting models there, and the controller LLM will point you to that specific algorithm. So this is the thing. For predictive analytics, it's very early stage. Any other question? Please use you can use your mic. We can save time.
Abbas sir, very good evening from India. Sorry to disturb you. You are using SQL or only any PDF file knowledge base regarding your descriptive analysis?
Actually, if databases are coming up, we have a lot of controllers written. If databases are coming up straight away, that's not a problem. If PDFs are coming up, we are sensing that tabular data is coming up. So we put it in pandas data frame, and then just use the other one. So we have different drivers. We parse either files are coming up, directly databases coming up, or other things. So in their respective data types, we are sensing them, parsing them, and putting them in their respective data types, and then extracting embeddings of those data sets once they are in the right format, and putting it into vector database so that anyone can query it.
That's very nice, sir. Thank you so much, sir.
Anyone
That's
else
from my end.
before? No worries. Yeah.
Thank you, sir.
Okay. Perfect. Thank you very much for your patience. And yeah, that's all.
Thank you so much, sir. It's a very good uh, talk, very useful.
Yeah, thank you. Yeah, thank you to Travers for the accepting the invitation and for very good talk and clarifying all the doubts and queries. Yeah, I think it's a really interesting session. So yeah, so maybe we can move to the next session. Yeah, Kusamlata madam, you can continue.
Yes, sir. Okay, so the next session is about LLM inference and deployment. So Mr. Sambit, along with the Shahid and Mr. Debasish, they are going to jointly present on the how to deploy an inference of a large language model. This will also include the hands-on session, which is focusing on LLM inference and deployment. So I would like to invite Mr. Sambit along with the Shahid and Debashish.
Just a minute. Okay. Okay, all right. So hello, in this presentation, mostly I'll be presenting. So I am Debasish, so thank you for being with me. So this session will be mostly focused on how to use an LLM once it is ready. So let's begin with the agenda. As you can see that from the agenda that will be mostly focusing on inference and quantization. So let's see what those things are. Let's begin with the terminologies. So as we have already discussed extensively in this workshop, LLM, those are large language models. What is quantization? So as we see, LLM is basically a massive neural network that is made up of weights, adapters, etc. So those weights have different precisions. We can store them as integers, we can store them as floats of different precisions. So the quantization is the process of decreasing the precision of those weights so that the size of the LLMs could decrease. What is GPTQ, AWQ, RTN? Those are basically different methods of quantization. And GGUF, this is basically a format in which LLMs are stored. You can, in Hugging Face, you can find many models being stored in this format. So let's begin with inference. So let's say we have a LLM that we're happy to use. So be it pre-trained or a fine-tuned model. So how to use this? The process of using a LLM to generate output is called inference. So while using an LLM, we focus on three parameters. Three parameters are speed, accuracy, and resource utilization. The first two, that is speed and accuracy, those two should be as high as possible while keeping the resource utilization under a limit that should be affordable by either by a person or a company. So these are the key metrics for LLM serving. So let's say we give a certain prompt to the LLM. The time it takes to generate the first token or the first word is called the time to first token. The average time taken by the LLM to generate one output token is called the time per output token. The total time taken by the LLM to generate the entire output is called latency. While LLM is not being used by a single person, it is used by many persons across the world. So the total number of words it can produce per second across all the users across the world is known as throughput. So let's begin with quantization. Let's begin with what are 4-bit and 8-bit inference. So as I had already explained, LLMs are massive neural networks, so those weights can have different precisions, and those precisions can be are essentially they determine how much space and how much hardware the LLM will consume during its inference. So these are two popular formats of LLM inference. So these are 4-bit and 8-bit. So what are their benefits? So what they do is they speed up the inference time of the LLM, and they also reduce the required hardware for the LLM. These are the benefits, and the challenges are as we are decreasing the precision, it also takes a toll on the performance of the LLM. So we need to find a certain trade-off between these benefits and challenges so that our hardware resource is minimal and our decrease in performance is not that bad. Let's begin with quantization. This is, I had already explained, this is the reduction in precision of the model's weights. So here is an example. So this is the full precision, that is float point 16, and this is the quantized version, that is int4. You can see the dramatic reduction in the model size. So here the Llama 2 7 billion, it takes this much amount, 13.5 GB, and while in the quantized version it takes only 3.9 GB. So it's roughly a 4 times reduction in hardware requirement. So it reduces the latency and the storage, and as a side effect, it takes a toll on the performance. What is Llama CPP? So this is not related to this is related to quantization, but it's not exactly quantization. So it's basically a CPU-centric library that lets you run the LLM models on your local computer. Initially, it was designed to run Llama models, but now it offers various other models as well. So it's written in a very low-level language so that it doesn't have dependencies such as NumPy or those things, so that the inference will be faster. So as you can see, this one is running on a CPU in a MacBook, and this is running a LLM with 13 billion parameters. But see the inference time, it's just 10 seconds. It's quite fast. And while used in MacBook, it's faster than ChatGPT. But the downside is that since it is 4-bit quantized, the performance takes a toll. And this is similar to Llama CPP. This is not a library, but a full-blown software. You will install this software on your computer. You will choose a model. This software will download the model on your computer and run it using the 4-bit quantized version. You don't even require the internet once you have downloaded the model to run the model using this Llama Studio. And this is the first version of GPTQ. So here what we do is that we have a float point 16 weights. So we convert those weights into integers so that the space required is less. And while this transformation from float to integer, it should be carried in such a way that the decrease in performance is minimal. And here you can see the comparative performance. The dark one is the full precision LLM, while the 4-bit GPTQ is the 4-bit quantized version. As you can see, the performance is almost similar, just a little bit lower than the full precision version, but it's almost similar. So this was quite a recent paper. You can check this out. It's in the resources. This is the second version of AWQ. So the basic fundamental of this method is that, let's say we have 1000 parameters, 1000 parameters or 1000 weights in a model. So this states that not all the weights are important. So what you need to do is you just need to find out this 0.1 to 1% of all the weights that are extremely important and need to safeguard this. So you do not convert those tiny minority of weights into integer format. The rest of the weights, they can be converted into int4 format without a problem. But as long as we identify those critical weights and conserve them, the performance, the decrease in performance will be dramatically lower. You can see. So So here is the AWQ W4A16 format, the red one, and here is the FP16 format. So this is the tokens per second. So if you are using this FP16, of course, the hardware with the same amount of hardware, the time taken would be more. So you can see that we are attaining up to a 4-fold increase in tokens per second if you are using this format, this AWQ. So, but the main problem is we need to identify what exactly are those weights that we need to conserve. So to identify those, we rely on activation distribution, and we do not rely on the magnitude of weights, but we rely on the activation distribution to identify which weights are critically important for the LLM. And this is VLL. So this is basically a library that helps us with fast inference of LLMs. So what it does is that it batches similar requests in a more efficient way so that the inference would be faster. And using this, we can attain up to a 24-fold increase in model inference without any need of retraining or anything. So here you can check we have built our own model that we are running using this 4-bit VLLM. We can show this. So let's see this. So the first question is, what is the capital of Mexico City? Correct answer, Mexico City. And the second question is, find the maximum element in a list. This is the correct answer as well. This is the third question. Write a poem about nature in Hindi. So the fourth question. What's your opinion on the development in artificial intelligence? And this is the fifth question. How did we fight against Corona? It basically says that we fought it through social distancing and better hygiene and all. So that was all. These are the references. So thank you. And before leaving, so I have one more thing. So I couldn't. So during the demonstration of the camel role play, I had a problem. So if you allow, I can show it right now. So there was a problem in this one. I was mistakenly running this one. So let's see. So this one is running fine. This one is the function. which is running fine as well. And here, let's say the user is a farmer, the assistant is a scientist. We want the task to be automatically determined. So let's begin. The task has been determined. The specified task has also been determined. And while it will take up to 2 minutes to generate the entire conversation. And while it's doing so, I have already shown it, but I'll show it again. So here we have explicitly mentioned the task. It worked fine. And here we have done everything with the extra step of translating the conversation into Indic languages. So here is the result. It's already past 1 minute. So hopefully within 1 minute, we'll have a result. Okay, so here is the conversation. So the user, that is the farmer, asks that to develop a certain mobile interface for which will help him in farming. So the scientist says that, okay, I will do this. The farmer again asks that collect field data to train the AI algorithm. The scientist says, okay, I will do this. So this is basically the idea behind it. Generate a task, a specified task, and iteratively call the GPT-3 to generate the conversation. So that was all from me. So thank you.
Yeah, thank you, Debasish. Yeah, I think now we are coming to the end of the session. I think there will be one more announcement. I think this will be the last session, and after this, I think we'll end it because the LLM use case that session we won't host. So so this one is the last session. I could see participants also, many participants are left now. And yeah, so this session I'll try to share my screen. So mostly I'll talk about RAG and I'll try to show more for hands-on, but yeah, I'll not, for the sake of time, I'll not run through everything. Is somebody can confirm is my slides are visible?
Yes, sir.
Okay, yeah, thanks. Yeah, so now we'll discuss about the RAG, which we call retrieval augmented generation. So if you look into the terminology, I think there will be two parts involved. One is the retrieval, and second one is the generation. So here is actually the agenda. So we'll discuss about RAG overview, like what is RAG and why it is required, and the main components of RAG, like the vector database or vector embeddings and such. What are the RAG components, and something about RAG evaluation and a use case. We'll discuss a use case. I think already Debasish has shown the Hindi model, like which we fine-tuned using Mistral. So maybe we can use the same model for RAG. So before that, actually, we'll go through a little bit about the issue or why we want the RAG. So yeah, these are the terminologies I'm using. As this is my last session, I think now you have already acquainted with the most of the terminologies, like but still I think these terminologies I'll also explain, like what is vector database or embeddings or chunking or retriever generator. So maybe before starting, I'll just explain a little bit. So vector, I think already you know, like now I think in the very beginning session, so I think he explained that, okay, these algorithms, they don't understand any text. For example, if you say any query, you are inputting any query that, okay, what is the capital of India or something, whatever the text you enter to the systems or these algorithms, they don't understand really any natural languages. So they all will be like in boiled down in to some vectors. That means we are finally actually we are representing all this text actually into a vector forms. So like how we are converting, I think that will be a different topics. I'll not go deep into that, but assume like we are all the sentences or the words we are converting into equal vectors. And to store those vectors, okay, we need a vector database. Like your normal database, you are storing different data types, like for example strings or integers. Now assume, okay, for we are storing in a vector database all these vectors. And also this vector embedding, as I said, this embedding is nothing but the representation or the numerical representation of those sentences. And also we'll discuss something about chunking. Even I think in the previous session we are discussing about, like if I have a 100 page of document, then how I can input to these LLMs. So where actually the chunking is nothing but actually we are splitting it. For example, you want to split those things into a set of documents or a small set, then you can input it, or from the small set you can get the embeddings and you can input it. So that will be chunking. And here actually two main components we'll discuss. One is the retriever and second one is the generator. So retriever is a nothing but when we say that, okay, we want to when we say that, okay, we want to extract something or extract the context, then we call it like the retriever. So retriever is nothing but actually we'll see in subsequent slides. Actually, it is nothing but when you are putting some text, actually it will try to find out the similar similar context or the matching content. And as we know, as I told, like in the beginning, or this algorithm, they don't understand anything apart from only vectors. Then how will match? Then mostly, like for example, we use some mathematical algorithms. It will be based on like some cosine similarity, or it will be like mostly like it will be vector operations, like where we try to say that, okay, if the numerical representation of this vector, okay, try to find out other similar vectors which will be matched to this particular vector. So in that way, actually, we are trying to retrieve the similar words or similar sentences. So that will be done by this retriever or this component of retriever. And the generator is like when we are generating the content, like you are putting or you are passing some query to the LLMs, and LLM will generate the contents. Like in the first session, we have shown like so I think he has explained like different algorithms, like how the different models architectures, like the encoder decoder, like how it generate the text. So that will be like part of the generator. So like as we, these are like a language models, so there it knows that, okay, how to generate based on the context. So for example, if you are passing a queries and a context, then by taking into consideration, okay, then how I can generate the next sentence or next word. So that will be part of the generator. So we need to understand this terminology, then I think it will be useful for all the subsequent slides, like for vector database, where you want to store the vectors, and vector embeddings are nothing but the representation of your sentences in a mathematical form, like in some vectors, and chunking is for splitting the long context, and retriever is a component which will try to, if you put some text, it will try to find out the matching text. And the generator is nothing but if you pass some input, it will generate based on your query, or based on your query, it will query or questions, it will try to generate the next set of sentences. So this terminology, okay, I have explained. So based on this, actually, we'll discuss. So why RAG? I think in now I think it's means more popular. RAG is more popular, and people are using it RAG. So as we have seen, like this, all these like models, which we call like the foundation models or LLMs, actually, they have their own limitations. So one of the major limitation of this language models are actually they have they mostly they respond with the answers related to the data they have seen. And that also, I think they also follow some timelines. I think you have seen, like we say that, okay, chat gpt is trained up to 2021 data. That means if you when a few days back we are learning, and every day by day actually it is improving. So when we say that, okay, it is trained on to data of 2021, that means if you ask any recent questions, then it failed to answer. So that one will be more one of the major drawback. So for something is happened just now, and you are trying to ask chat gpt or llm, if it doesn't have any idea, then it won't able to answer. So that will be the major problem with this foundation models. And and another actually issue is like that, when we say that, okay, maybe to overcome these limitations, when we say that, okay, we can do fine tuning these models, like with some additional data, or we can build some specialized model. We'll take some base models, and we can provide some additional data. That is also possible, for example, but that also comes with a additional cost. For example, these fine tuning costs are not so means not so cheap. I think in the previous session, Dr. Abbas, he also mentioned, like, given some hint, like how much cost incurred for fine tuning all these models. And also it needs a, and how much time, another question is like how much times you will do the fine tunings, or how many versions. For example, today some data comes, again tomorrow will data, then how long you will do this fine tuning process. For example, you will do the fine tuning for every month, or every 15 days, or every week. So that is also another challenge. So I think I have highlighted, there are also many other limitations are involved, but these are like some of the major limitations why we want to go for RAG. So when we say that, okay, RAG, what is RAG? Already I told in the beginning, this will be like a retrieval augmented generation. Actually, it's a technique which enhance the accuracy and reliability of generative AI models with facts fetched from external sources. When you say external sources, that means it will be like it use the foundation models or the LLMs, and apart from that, also it use some other resources or other external source of information to to bring you the most accurate answer. So here actually the main important point about the accuracy and reliability. And that's why we say that RAG grounding LLMs on a set of external verifiable facts. The model has a fewer opportunity to pull information baked into its parameter. That means we mostly if we use this external informations, so this external information can be of different forms, or it will be in different from different sources. It can be from some financial report, or it can be from some verifiable website, or it can be from some kind of a document, or it can be some your internal report. So it can be anything, these resources, and it uses this information as an additional sources to provide you more accurate answer. So that is the key message. So, and this RAG reduces the need for user to continuously train the model on new data and update its parameter. So in that way, actually, you have solved the major problems or major limitations which we discussed in the previous slides. Like, you don't have to fine tune your model repeatedly, and you can also overcome all the limitations of the foundation model. That means now you have you can take any foundation model or any models, and you can also use some verifiable facts or other source of information, and you can input it and you can get the answer. So that will be the RAG. So next we'll see like how this RAG works. So I have taken a basic workflow. I have given the source. You can check the website also. The workflow, you can see the workflow. Actually, in the workflow, you can see like maybe we'll start from here. So assume I told like you need some other information, and these other informations can be in any form. Suppose, for example, assume you have a bunch of PDFs where, or some reports where you have all the facts are there. So you can use those as your external informations. So those PDFs, okay, those PDFs actually you can input, or you can extract the embedding from those PDFs, because as we know, like that your model there doesn't understand anything or any natural languages, they only understand the vectors. So next job is like, okay, we'll extract the embeddings from the PDFs, and then where we will store those embeddings. So for the storing the embeddings, okay, we are using a vector DB. So for example, as I said that, okay, these are like, we are vectors, okay, we store in a vector DB. So that will be like, assume it will be like a first part we have done. And second part is that like how we are querying to the LLM. So when you are querying the LLM, so earlier you said that directly we are passing the query to LLM. So in this case, what we do, okay, from the query also we'll pass to embedding models to get the embedding of the query. And from the actually query, we are trying to fetch the relevant or matching context. And so the matching context, as we know that already in the vector DB, we have vectors are there. So for example, based on different algorithms, it will be cosine similarity. So all the matching vectors means, for example, if you are searching for a what will be the best or a recipe for, or Indian cuisines you are checking. That means if you're in vector DB, all the related information is there, then definitely you can find all the matching context relating to the cuisine only. So we can get the relevant context which we say from this particular query. And now you have two input. Like for example, now you have the queries and you have some relevant context. Now you have the query and relevant context. And earlier, what you are passing directly query to the LLM, but now you are passing to the query and plus the context to the LLMs, and you will obtain the response. So that will be the whole idea. So same thing actually I have written in the workflow. It is written, so I have taken from here. You can go through that blog post. It will be nicely explained. So in the first phase, we are receiving a query from the user. Then we are converting it to an embedding query vector. We are preserving the semantics. We are retrieving the top key. So in the top key, what we say when we say that, okay, we are trying to matching context. So this matching context actually, it can be matched. For example, if it will be a lot of documents are there, so it can be matched with many vectors. So which one to choose? So for that, actually, we are using something called top key. For example, some default value, if we set, okay, we'll use the top 4 or top 5 relevant context, then based on that, okay, it will fetch, and we are passing them using the along with the query to get the answers. So same thing. So and also pass the retrieved content and query as a prompt to an LLM, and the LLM gives the required response. So I think that is the overall workflow of RAG. So now, when you are talking about a use case, for example, you are asking something relating to, assume a share market information. So, for example, like maybe if your model is trained for share market information up to let it be 2022. Now you have all the financial reports available up to all the updated information of 2023. Now, what you can do, you can create some embedding models and store in a vector DB. Now you using the model or the foundation model which is has the information up to 2022, you provide any queries, and then what happened, the query will be there, but from the embeddings model, like all the latest context information or the reports up to 2023, you get many matching context, and then okay, you can able to answer it correctly even if your model has not seen those data, but you can but still it is able to provide you right answer. So that is the idea. And in RAG, these are actually two major components. One is the retriever and second one is the generator. In the retriever, it searches through the large knowledge source and retrieve relevant context passes from the given query or task. So it will just find out the relevant context. And the second one is the generator. So generator, actually it will be it will generate your answers, putting into the LLM or passing the both query and context to the LLM. So these two are the major components, and all the performance of RAGs depends on these two. So either, for example, when we are trying to say that okay, now a lot of research is happening on in RAG, like many companies. So they try to improve the performance of retriever or generator. So mostly actually the major research is going on this part, in the retriever part, like how I can efficiently retrieve the context, because based on that actually all the RAG performance depends. So maybe some recent approach we can discuss, or some recent topics which is in interest we can discuss subsequently. Okay, now we know that okay, in RAG there are two components are involved. Main is a retriever and another is a generator. And also we know that okay, these vectors actually we are storing in a vector DB. So so we'll just discuss little bit about vector database, because we know about the database, like traditional database or RDBMS, like we are storing like the numbers, a string, or some floating point numbers, or some kind of blob or some images in different formats. So what is this? So this one, if you know, this is like we are storing in vectors. So this vectors means it is nothing only for the text, it can be anything. For example, it will be like, for example, from image transformer you can convert into image into vectors, or it will be like from text into vectors, or some audio format we are converting into vector. So all kind of vectors, okay, we are storing in a vector database. So the vector database, it's a type of database that indexes and stores vector embeddings for fast retrieval and similarity search. So why we are storing in this vector database? So that actually we can search the database very fast, and that actually improve the performance. So that actually all the embeddings it will be stored, and it can be also retrieved very fast based on the similarity search. And one of the key important point here is like the power of vector database lies in the unique data, which we call the indexing. I think in the database, the indexing is one of the key terms. Like based on the indexing, actually we are using to retrieve the contents. So the indexing actually lies. The measure, like the performance of the database, actually lies in indexing, and mostly they are designed in such a way that they can do the similarity searches. So like for example, when we are passing some query, so it can, from a very large database, maybe it will be like from million of documents you have done some embeddings that store it, so that how fast it should retrieve. means it should not retrieve like a half an hour or 1 hour, then okay, all your performance will be degraded. So how fast you can retrieve? So those actually lies in these algorithms like indexing. And also actually in the indexing, actually there is a, it's actually very broad topic, so I'll not go into much details, but whatever is required I'll just tell so that it will be easy to understand. So there are actually a lot of indexing algorithms we are using. So you might have seen like in various vector DBs are available, maybe Pinecone is available, or Chroma is available, or Vertex is available, or Waveate is available. So all this actually how they differ. Actually, mostly they differ in these terminologies, like how they are storing the data or how they are indexing the data. So that we can say that okay, this vector DB is perform better than other. So now that is one of the major research topic or research area which we are doing. So this vector database they are used. This is not only using in LLMs. Actually, they are using in AI, machine learning, or NLP, or image recognition. So in many applications, they are using this vector DB. And if we go boil down to that, like in the vector DB, like when we are searching, the majorly it will be using this kind of similarity matching. So if you look into like the vector embeddings, as I told, like for example, different words are there, like animals, wolf, dog, cat, query. So if you look into like in the semantic search space, if you try to project them, if you find that okay, all the similar items will be close together. Like in the animal, like this will be like we can see the clusters, like the animals are all together here, or fruits are here. So for example, like if you want to search something like, for example, something related to animals, then you can easily retrieve from there. So vector embeddings, so they are actually convert the word and sentences and other data into numbers that capture their meaning and relationship. As already I explained, and in vector indexing, it is a process of organizing vector embeddings in a way data can be retrieved efficiently. Already I told, and also this numerical representation of data object allows to apply mathematical operation. So in the mathematical operation, as I said that okay, mostly we are using different mathematical operation. Like for example, when you say that this will be it will be like based on cosine similarity. Cosine similarity means okay, if these two vectors are how close they are, or like for example, we are finding out in the difference in the Euclidean distance matrix, in Euclidean distance matrix or Manhattan. So actually these are like different matrices we are using. So these actually all depends on the what we can call the implementation of this vector DB, and based on these matrices actually their performance depends. So we'll not go into much details, but just to get an idea like that, okay, how when we are trying to search similar elements, how it comes. Actually, these are based on this because we are storing into these vectors, and when we are passing some new, for example, new queries, again it will convert into the vectors, and that vectors will try to match, like okay, for example, if it is relating to animal, then definitely it will become these vectors will be retrieved because these are actually similar. And chunking, I told a little bit about chunking. Like for example, why we want to chunking? For example, it's not possible to store very large documents. So that actually we need to do some kind of chunking, means some kind of splitting, or it will be like this input text we have to split into some meaningful units. So that will be actually comes into chunking, and there are actually different parameters are involved. Like for example, how much chunk. For example, if we are assuming 1,000 page document, then for example, how we can split it. Like for example, what will be the size. So that actually also another criteria. So each chunk, when we say that, it will be like a unit of information that is vectorized and stored in the database. And this chunking actually important for optimizing the RAG. For example, when we say that okay, we want to retrieve the context. For example, if it is be too large, then it will have some issue. Or if it will be like, for example, your chunking will be very small, then maybe it will lose the context. So that actually depends on your optimization of the RAG. So as you say, using short chunks, you can add information from more chunks to the LLM. However, it may lead to inefficient contextual information being passed to each result to the LLM. Or larger chunk would mean fewer chunk would fit into the context window of the LLM or incur additional cost. So that will be like it means it will be like what we call, it will be like a deciding factor, like what will be your ideal chunk size. And also we take another parameters like the overlap, like with chunking, like for example, how many uh, how many you need to be overlap. For example, maybe in a 2000 chunk size, maybe if you can take that, okay, 100 100 tokens can be overlap. Yeah, so now actually going for a use case, what we are will show in the demo. So it will be based on this retriever. So there are like a different type of retrievers are there. I think in the previous slide someone was asking about about this big document. Like if it is a very big document, then how we can pass it. So there are actually different retriever mechanisms are available, like parent document retriever or self-querying or wave research retriever. So quickly I'll go through it. So in the parent document retriever, like as we know that, okay, it will be like it's a balancing criteria about splitting the document. So for that, actually maybe this parent document retriever will be ideal. Like in the parent document retriever, it strikes the balance by splitting and storing small chunks of data. So if you look into, actually this will be the original document. So in the original document, actually it will be split into some chunks, like the parent chunks, and parent chunks is nothing but some larger chunks. And again, these parent chunks will be split into some child chunks, which will be more granular. And uh, actually these chunks, actually when we are trying to retrieve the context, actually we are using both. For example, like we are starting from the child chunks, and again we are referring to the parent chunks to get it, and finally we are passing to the LLMs. So this one will be like one of the retriever mechanism. Also people are using self-querying, where self-querying retriever is one that where it has the ability to query itself. So that one will be mostly using self-querying. Also, like people are using like web research retriever, like where you can try to search web for different search criteria. For example, you can search in Google searches, and you can load all the resulting URL. Then you can get the embedding and perform similarity search based on the query and the page content retrieved from the URL. So that is also another popular. So these are like some of the retrieval mechanism which we are using. So based on your like use case, you have to select appropriate retriever. So okay, retriever is fine. Like now assume that, okay, we have retrieved the context. The next task is like, okay, the evaluation matrix. So like how we can evaluate. So for evaluation, actually there are different mechanisms are there. Like we can start from some traditional matrices like cosine similarity, which where we can it will help to understand the similar vectors. Or also we can use bot score, like for the semantic similarity. Both are like similar. In bot score, mostly we are seeing that, okay, how semantically the output is matching with the ground truth. And also nowadays these LLM based matrices are quite popular, because what we found, like when we are generating the text using LLM, these traditional matrices are not much suitable, where these LLM based matrices will come into picture. Like recently, okay, this ragas is there, where people are using for LLM based matrices. In the ragas, actually the good part is like that, okay, it will try to evaluate both. It will try to evaluate the retrieval and as well as the generation. So for example, in the retrieval part, actually it will try to evaluate the context, how good your context is. So it will check the context precision, like the signal to noise ratio of retrieved context. and also it will say have a context recall. Can it retrieve all the relevant information required to answer the question? That means whether you whatever context you have retrieved, whether that is sufficient to answer the queries or not. So, and also it evaluate the generation part, like the faithfulness, like okay, how factual accurate the generation answer is, or how the answer is relevant. So these are like LLM based matrices. When I said LLM based matrices, means actually these matrices or these matrices actually internally use LLMs. That means if you want to use these matrices like Ragas, then you need OpenAI or ChatGPT. And internally, actually, it uses the prompt to evaluate it. And one way it is good, like okay, you'll get more accurate answer as compared to your traditional matrices, but at the same times it incur cost. For example, from our experience, okay, maybe for if you are it will take around 2 to 3 times more tokens it will consume to generate the scores. So but these are like, as I said, those are like more popular, sorry, more accurate. For example, like it can tell you the faithfulness, like it can check the exact factual consistency of the generated answer. For example, if you say that okay, where and when was Einstein was born, the context say that okay, Albert Einstein born 14th March 1879. So the faithful answer will be okay, it will be like 14th March 1879, which is closely, it will, the fact is correct. So that will be like it can check the faithfulness. Whereas if it will be 20th March, okay, it will not correct. Or it will be the check the answer relevance, like the answer relevance, it focus on assessing how pertinent the generated answer is to the given prompt. So like where is France and what is its capital? France is in Western Europe. So this will be not very relevance answer, where the high relevance will be France is in Western Europe and Paris its capital. Also, it will check the context precision, like how the context precision. It actually it evaluates whether all the ground truth relevant items present in the context. That means whatever your ground truth is there, it will also consider that, and it will check that whenever you are retrieving the context, whether those how closely it is matched. So that will be in the context precision. Also in the context relevance, like how relevance is your context. For example, okay, it will check that okay, the relevancy of the retrieved context, and it will be calculated based on the questions and the context. So you can see that okay, what is the capital of France? The high context relevance is this one, and low context relevance is that okay, it says that, but also it talks so many things which is not relevant. So it says that okay, the context relevancy, what will be the its score, or context recall, measure the how extent to which the retrieved context align with the annotated answer or treated with the ground truth. So that also checks in the context recall. So these are like the some of the matrices which we can use. So before going into the demo, so do you have anyone has any question to ask? I don't know how much time we have. Otherwise, quickly. Uh, Actually, I'll share the notebook, so you can hope my notebook is shown. So I'll not run the cell one by one due to the time. It will be, I don't think it will be uh, feasible. But yeah, so actually for the experiment session, actually we have use a the parent document retriever. So in the parent document retriever, I told you like what will be the advantage and disadvantage of small and long long chunks. And so using that actually parent retrieval, actually we are and for this experiment setup, one more thing I think so. Actually, in the demo part, maybe I could show. In the demo, actually, we are using this parent document retriever, and we are using the LLM as a Mistral 7B Hindi model, and Labini as embedding vectors, and OpenAI for embeddings. Yeah, so I can quickly go through the collab. We will share the collab notebook for you can try it. So first thing is that okay, we have some set of document or the input document. So you can see that these input documents are the Hindi text, and then actually we are using a as I said that we are using our model. So our model is the Hindi Mistral 7B model, which Debasish was showing the demo. And then actually in this part, actually we are trying to 1 second, 1 minute. Excuse me. Yeah. Yeah, actually, here actually we are using the in the Mistral 7B model, like it is already available in Hugging Face. So here actually we are loading the model, and so we are just testing the model. So you can see that the model is loaded. So I don't want to load it the model, and so we are just testing the model by providing a question with a context and the answer. So you can see that, okay, if you try to provide a questions and with a context, then it can provide the answer. For example, we have given some instructions, and with for example, our question is about घोषणा की तारीख क्या है. That means what will be the date of announcement. Then it says that, okay, घोषणा की तारीख 10 अगस्त 2021 है. That means, okay, it will be, the answer is correct. That means the model is running. Actually, then actually we are trying to do it. As I said, for this experiment, actually we are using a Lamini like V2. Actually, it's for storing the embeddings, and so we are retrieving the embeddings and storing it. So here actually it comes into the picture, the parent child. So first it's like we are splitting it. The text splitter is used to create a child document. So here actually we are trying to split into using this recursive character text splitter. With we are providing a chunk size of 200, and it will actually, the vector store used to index the child chunks. It will store the child chunks in vectors. And also, as you said, that it also involves a parent, where it stored the larger chunks into the memory of parents. So this will be for the parents. And here actually we are having a full document retriever. So that one will be for the parent document retriever. If you look into, actually there will be vector store for all the child chunks, and also for a parent document retriever. So here actually, if you look into the full document retriever add document, so they have actually some, you can see, find some keys. So these keys actually nothing but they are used to having the matching with the parent vectors to split, means retrieving the context. I think maybe you can relating with this part. For example, you have a child chunks embeddings are there. Also, you have a parent chunks. So you can retrieve using this. So in the example, also you can see, for example, we are providing a vector similarity search. So this one will be for the child chunks. Like you retrieve all the relevant or embeddings matching with this Bharatiya Samvidhan kab lagu hua tha. Then it can able to retrieve. So similarly, actually, if we want to retrieve the full context, that means full context means your parent has all the large chunks. So here actually we are retrieving full document retriever, get relevant context. So if you pass it, then it will give you all the larger chunks. It can retrieve. So yeah, so you are providing it the two similar questions, and here actually we are trying to retrieve. So retrieve. Before for retrieving, actually we are using the LLMs. So LLM actually we are using, as I said, a Mistral 7B, and here you can specify the chain type, and it will be retriever. We are retrieving like the full document retriever we are passing, and then actually it will try to retrieve. For example, query will be like Uttar Pradesh ka pehla mukhyamantri kaun hai. Then here you can see that, okay, the retrieval process. I think this debugger is on. That's why it will be give you the exact messages, like how it works. So here actually, if it will be not, if the it will be not match. For example, whatever the query you are answering, it will be neither it will be in the model or in the context, then it won't be available in the result. For example, if we ask another questions, like for example, here we are asking like the query will be Jhansi ki Rani kaun thi, then it will try to fetch the answer. Okay, like the झांसी की रानी लक्ष्मीबाई थी, यह झांसी के राजा की पत्नी थी और उन्होंने विद्रोह के दौरान ब्रिटिश सेना के साथ लड़ाई लड़ी थी. So this one actually you can play around. So I just shown one simple retriever, but I suggest like you can play with a different type of retriever, like a self-querying web search retriever, and also you can play with a different type of embedding vectors. Like for example, you can play with chroma, or lamini is like the very simple one, but you can play with chroma, or you can play with waveit, and you can do some experiment to see that how it works. So I think this one will be some introduction you might have got about the retriever or how it works. So here I can stop sharing, but if you have some questions, maybe we can take and end the session. I think it will be a long session now. I don't know how many people are there. Yeah, thank you. So anyone has any questions or queries?
Yeah. So thanks for the session. Actually, I got a lot of insights to this. I have a question. Like when you're dealing with a mixed type of documents, like some are Word documents and some are CSVs. So CSV are literally like single line documents. So while doing a retrieval, we have limitations. Like we can like return top 3 or top 4. And in that case, like which retrieval will be most optimal?
Yeah, actually, when you have a mixed set of documents, actually, generally we use. Actually, there are two approaches are there. Like one thing is like what you can do. Like for example, if you could make all your different type of data into a common or uniform data and get the embeddings and store in a vector DB. That one will be one option. And second option is like that. Sometimes we use this multi-step RAG. I don't know if you heard that multi-step RAG. Like for example, here instead of RAG, like we try to split into different forms. Like for example, assume you have records or you have data. So in the data, some data are just plain text, some data are in some tabular, some data are in some image form. So in those cases, actually we do some multi steps. For example, in your case, for example, some data are in assume it will be like a different only plain texts are there. Some data are maybe in some different symbols or characters or some in a different format. So maybe you can use multi-step RAG, or either that is one option, or second option, as I said, maybe you can try to uniform. But I don't know, like it will be like it will be based on the your exact problem what you want to solve. Maybe.
Yeah. Thank you. So we'll definitely catch up on this. Okay.
Yeah. Okay. Yeah, if you have any questions, so I think yeah, we can take 1 to 2 questions. Otherwise, actually, we can end the session. So I think thank you all for joining, and I think it's a long session.
Sir,
So yeah.
thank you, sir. Sir, I have a question, sir. How to remove the biases if it incur in the vector databases, if any? Then the RAG will fetch those biases in that answer.
Yeah, actually, yeah, exactly. That is a very good question. Actually, biases will be there. That's why actually, as I shown this matrices like the ragas and other matrices are there. Actually, those matrices can give you some hint, like whatever the data you are extracting, actually that is not correct, or some issue with your extractor. Like for example, in the context relevancy, or for example, you want to extract, you are extracting the context, but those are actually not nowhere it is relevance, or it will be unnecessary some noise you are getting. Then I think that one will be you can get some indication from the matrices if we use. But as I said, these matrices also costly because it require a lot of consumption of OpenAI tokens. Yeah, but yeah, it is possible to, at least it is possible to know that okay, there's some issue with your data. And second part is like that, if you know, once you identify that okay, my data has some issue, then probably you can you could work on how to improve it. For example, the improvement point is like for example, maybe you can go for multi steps, or you can do some, people are also trying with the prompt engineering, like they are trying to find out the context using different, applying different kind of prompt. Or people are trying to use as I said, that splitting, for example, as even Abbas was telling, like they are like, for example, they are not passing a single query. Instead of single query, okay, where they are trying to split into multiple queries, and into different kind of information. First they are trying to collect, and they are framing the query, and they are passing. So there are actually many approaches are there you can try. But yeah, there will be no, I can say there will be no a single single or standard rule for this. Okay.
Thank you, sir.
Yeah, thank you. Yeah, so yeah, I think we are at the end. So it will be now we are ending the session. So yeah, I think all the technical questions will not discuss more. But yeah, if you have some general feedback about the workshop or anything, feel free to provide. And I think all the necessary information we have shared in the chat and group. Yeah, so yeah, then maybe we can. If somebody has any feedback.
Bye. Thank you very much. The sessions were informative.
Oh, okay. Yeah. Yeah, I hope, yeah, everybody has some learning. And definitely it's like I think it's together we are learning each other, means trying to get new things. And I think also I'd like to thanks all the interns and all those who have contributed to, they have actually spent a lot of time for preparing the session. So yeah, thank you very much. And also those who have joined, also I'd like to thank. And yeah, feel free to contact us if you need anything. Yeah, so maybe Debasish, you can stop recording, and we can end the session here. And maybe yeah, for feedback, feel free to provide them.
We'll pass on.